Our universe is filled with wonders. Some are visible, like the countless stars scattered across the night sky. Today, we journey into the realm of organic chemistry, focusing on a fascinating group of compounds known as alkenes. Alkenes are hydrocarbons, built from the fundamental elements of life, carbon and hydrogen. What distinguishes alkenes is the presence of a carbon-carbon double bond within their molecular structure. This double bond dictates the personality of these molecules, influencing their properties and reactivity. The general formula for Alkenes is CnH2n, where N represents the number of carbon atoms. Join me as we delve deeper into the world of alkenes. In the world of organic chemistry, the concept of unsaturation is paramount. It distinguishes alkenes from alkenes, dictating their chemical behavior. Unsaturation refers to the presence of double or triple bonds between carbon atoms within a molecule. Alkenes, with their characteristic carbon-carbon double bond, are classified as unsaturated hydrocarbons. This means they have fewer hydrogen atoms than their fully saturated counterparts, the alkenes. In alkenes, all carbon atoms are fully saturated with hydrogen atoms, forming 4 single bonds. However, in alkenes, the presence of a double bond means they are not fully saturated with hydrogen. This unsaturation is the key to their unique reactivity. Like celestial objects in the vast universe, each organic compound has a unique name and identity. The International Union of Pure and Applied Chemistry, IUPAC, has established a systematic method for naming organic compounds. To name an alkene using the IUPAC system, follow these steps. First, identify the longest carbon chain containing the double bond. This chain forms the parent name of the alkene. For example, a chain with 2 carbons is called eth, and a chain with 3 carbons is called prop. Next, number the carbon atoms in the parent chain, starting from the end closest to the double bond. This gives the double bond the lowest possible number. For example, if the double bond is between the first and second carbon, the name will include 1ene. Then, identify and name any substituent branches attached to the parent chain. Finally, combine the parent name, double bond position, and substituent names to form the complete IUPAC name. Mastering the IUPAC nomenclature is like learning a new language, allowing chemists worldwide to communicate effectively. The double bond in alkenes not only governs their chemical reactivity, but also influences their physical properties. These properties, including boiling point and solubility, are a direct consequence of the molecular structure and the forces between molecules. Alkenes, like alkenes, are nonpolar molecules, primarily experiencing weak van der Waals forces. However, the presence of the double bond introduces a degree of rigidity into the molecule, affecting its shape and packing. Generally, alkenes have slightly lower boiling points compared to alkenes with the same number of carbon atoms. This is because the rigidity of the double bond hinders efficient packing, leading to slightly weaker intermolecular forces. Alkenes, being nonpolar, follow the general rule of dissolves, meaning they are soluble in nonpolar solvents, like hexane and benzene. Understanding the physical properties of alkenes is crucial in various applications. The double bond in alkene is not merely a structural feature, it is the heart of their chemical personality. This electron-rich region acts as a center of reactivity, readily attracting electron-seeking species known as electrophiles. The double bond consists of 2 types of bonds, a strong sigma bond and a weaker pi bond. The pi bond, with its loosely held electrons, is the key player in the reactivity of alkenes. When an electrophile approaches the double bond, the pi electrons are drawn towards it, leading to the formation of a new bond. This process is often accompanied by the breaking of the pi bond and the formation of a new sigma bond, resulting in the addition of atoms or groups of atoms across the double bond. This type of reaction, known as an addition reaction, is a hallmark of alkenes. It forms the basis for a wide range of chemical transformations, making alkenes versatile building blocks in organic synthesis. Hydrogenation involves the addition of hydrogen, H2, across the double bond of an alkene. This reaction transforms an unsaturated alkene into a saturated alkane, modifying its physical and chemical properties. The process of hydrogenation requires a catalyst, typically a finely divided metal like platinum, palladium, or nickel. The catalyst provides a surface for the reaction to occur, facilitating the adsorption of both hydrogen and the alkene onto its surface. Once adsorbed, the hydrogen molecule, H2, dissociates into reactive hydrogen atoms, H. These hydrogen atoms, still bound to the catalyst's surface, are then available to react with the double bond of the alkene. The addition of hydrogen atoms across the double bond is a stepwise process. One hydrogen atom adds to one carbon of the double bond, while the other hydrogen atom adds to the other carbon, effectively breaking the pi bond and forming two new CH sigma bonds. Hydrogenation has significant industrial applications, particularly in the food industry. Unsaturated fats containing carbon-carbon double bonds are often hydrogenated to convert them into saturated fats. Halogenation is another important addition reaction that alkenes undergo. In this reaction, a halogen molecule such as chlorine or bromine adds across the double bond of an alkene. The mechanism of halogenation involves a cyclic intermediate called a halonium ion. When the halogen molecule approaches the double bond, its electrons are repelled by the electron-rich pi bond. This repulsion induces a dipole in the halogen molecule, making one halogen atom partially positive and the other partially negative. The partially positive halogen atom then forms a bond with both carbon atoms of the double bond, resulting in a three-membered ring structure called a halonium ion. This intermediate is highly reactive and quickly opens up to form a new bond with a halide ion. Halogenation reactions are useful for various purposes, such as the bromine water test, to distinguish alkenes from alkanes. Hydration involves the addition of water across the double bond of an alkene. This reaction is particularly important because it introduces an alcohol functional group into the molecule, significantly expanding its chemical versatility. Unlike hydrogenation or halogenation, hydration reactions typically require an acidic catalyst to proceed at a practical rate. The acid catalyst, often sulfuric acid or phosphoric acid, protonates the water molecule, making it a more reactive electrophile. The protonated water molecule then attacks the double bond of the alkene, initiating a two-step mechanism. The first step involves the formation of a carbocation intermediate, where one of the carbon atoms of the double bond carries a positive charge. In the second step, a water molecule acts as a nucleophile, attacking the carbocation and forming a new carbon-oxygen bond. Hydration reactions are essential in various industrial processes, such as the production of ethanol from ethylene. Alkenes play vital roles in various industrial processes and are essential building blocks for countless everyday products. Their unique reactivity, stemming from the presence of the double bond, makes them versatile starting materials for a wide range of chemical transformations. One of the most significant applications of alkenes is in the production of polymers. Polymers are large molecules composed of repeating structural units called monomers. Alkenes, with their ability to undergo addition polymerization, are ideal monomers for creating a vast array of polymers with diverse properties. Polyethylene, one of the most common plastics worldwide, is produced by the polymerization of ethylene. This versatile polymer finds applications in packaging, films, bottles, and countless other products. Another important alkene, propylene, is the monomer for polypropylene, a polymer known for its strength, durability, and resistance to chemicals. Polypropylene is used in a wide variety of applications, including packaging, textiles, automotive components, and medical devices. Beyond polymers, alkenes are crucial in the production of various other chemicals. Ethylene oxide, produced by the oxidation of ethylene, is a key intermediate in the manufacturing of antifreeze, polyester fibers, and detergents. Our journey into the world of alkenes has taken us from the fundamental concepts of unsaturation and nomenclature to the intricate mechanisms of addition reactions and their vast industrial applications. We've explored the unique reactivity of the carbon-carbon double bond and witnessed its profound impact on the properties and behavior of these fascinating molecules. But our exploration is far from over. The realm of organic chemistry is vast and ever-expanding, with countless secrets waiting to be unlocked. As you continue your journey, remember that each reaction, each molecule, tells a story. Embrace the challenge of understanding these intricate processes. For within these seemingly invisible structures lie the keys to understanding the building blocks of life itself and unlocking the potential for a brighter future.